Okay, so yesterday we were trying to solve a problem, and we solved it using row reduction, right? So row reduction and Cramer's rule. But remember when we did the 2x2 system, we did have one last method called inverse method, right? So now it's time to learn how to do that in 3 dimensions and higher. Okay, so that's why we're titling it inverse matrix method. So remember the theory. The theory was that a system can be written as a matrix times xyz equals a matrix like that. And then if you wanted to get x, y, and z by itself, you would need to invert matrix A while bringing it over to the other side, like this. This is exactly the same notion as if you have 5 halves x equals 30, and you want to find x, you got to get rid of the 5 halves by inverting it and multiplying over. In other words, x is 2/5 times 30. 12. Right? Okay, so here's the question. How do you invert a matrix? Well, we saw how to do that with a 2x2. It's actually pretty easy. How do you do it with a 3x3? So let's go back to the question we were working on yesterday. And let's set up our matrix equation. That's this thing. This is called the matrix equation. Okay? Let's give it a try. All right, so here is our original problem. 2x minus 3y plus 4z equals 8. X plus 3y minus 2z equals negative 3. 3x minus y plus z is negative 1. You recall? Go ahead, please, and write the matrix equation version. Fill in the blank. Ready, go. Okay, so you should have placed the 2, the negative 3, the 4, the 1, the 3, the negative 2, the 3, the negative 1, and the 1 here, and then the 8, the negative 3, and the negative 1 here. Everyone have that correct? I think I copied that right. Always double check. Okay, now the idea is we should be able to get x, y, and z by itself if we can simply find the inverse matrix of our coefficient matrix. Then we'll just multiply it against the original 8, negative 3, negative 1 on the right. Okay, so here's the problem. When I first saw this, I just assumed you could just like do reciprocals or something. You know, my first time I ever saw it, I was like, oh, I know what I'll do. I'll just do like, I'll just change the 2 to a half, right? I'll change the 3 to negative 1/3, the negative 3, that'll become a 1/4. It's not quite that simple, folks. Okay? I'm not saying find the reciprocal of every term. That's not quite how we do it. So how do we do this? It's a 4-stage process just to get the red thing figured out. So we're going to take a detour from this slide, okay? We'll come back to this later when we have the red thing figured out. But how do we get this thing? That's what the next 10 minutes is about, all right? Everybody ready? Here goes. To find the inverse matrix, just think these 4 steps. 1, find a matrix of minors. Find the matrix of minors. Okay? 2, find or form the matrix of cofactors. This will all make sense to you in a minute, okay? Third, find the adjoint matrix. And fourth, divide each element by the determinant of the original matrix. Okay, now, a little comment about this last step. You might want to do this one first. You might want to find, at least, the determinant first. Here's why. If the determinant happens to be 0, you are wasting your time with this method. Okay? Let's say that you do steps 1, 2, and 3. It takes you 10 minutes. You finally get it all done. You go on to do step 4. You discover the determinant was 0 all along. You can't divide by that. See the problem? So it's probably wise to just double check at the beginning of a problem, is my determinant 0? Because if it is, I'm wasting my time doing steps 1, 2, and 3. Okay, so that's kind of just a rule of thumb. Cramer's rule is the same way. You know, you got to find d sub x, d sub y, d sub z, and d. Why don't you find d first and see if this problem even makes sense? Okay? All right, so let's just go ahead and run through these steps. All right, here was the matrix that we're trying to invert. Okay, the first step was find a matrix of minors. Find the matrix of minors. Matrix of minors. Mom. Okay, think parents and children. Okay, minors are the children. Okay, so we start with the 2 in the top left corner. So I'll use my highlighter for this part. You're going to focus on this 2. Okay, find its baby. Who's its baby? Who's the minor? Where's the minor? This stuff, right? I need the determinant. Find the determinant of that right there. Go ahead. Find the determinant of that. That's the baby in green. Okay, find the determinant. It's 1, right? It's 3 and 2 are the product, and you're subtracting, right? The products are 3 and 2. You're subtracting. The child is 1. Okay? You know what that means? The first of 9 elements in our matrix of minors is 1. Where'd I get it? It is the child of element 1. It is the child of element 1. Okay, next is the negative 3. Where's the baby? Yeah, this stuff here in blue, right? I need the determinant. Find the baby. The products are 1 and negative 6. Remember, you're subtracting. So what is it? 7. Child number 2 goes in space number 2. Who's the next mother or father? Who's the next parent? The 4. Focus on the 4. Find the child. I should say find the determinant of the child, right? There's the child there. Find the determinant. What? Negative 10. Yes. -1 and 9, and you're subtracting. The third child goes in the third spot. On to the fourth child. The fourth mother, technically. The fourth mother here has a child too. Where is it? Okay, so to see the child more clearly, watch close. To see the child more clearly, just cross out the row and column that the mother lives in. Okay, so you cross out the mother, you cross out the row of the mother, you cross out the column of the mother. Do you see the child now? Here's your child right here. I want the determinant. Now notice, you're still multiplying this way. Okay? So you still do -3 for your first product and -4 for your second product. So you still multiply that way first and then that way first, even though you're kind of straddling that line, it doesn't matter. So we have -3 and we have -4, but we're subtracting, so that comes out to what? No, don't criticize the method. It works in all dimensions. Okay? And not everybody likes row reduction or Cramer's rule.
Well, this is like doing like...
Also remember, Cramer's rule doesn't give us the actual inverse matrix, which on its own is meaningful. It's meaningful to know the reciprocal of something. That's always meaningful. What is the determinant of the child in this case? What's -3 take away -4? What is it? 1, right. So it's getting a little harder to see your parents and children here. But we are on to our middle box of our final answer. So that means we will be treating this as the parent and crossing out the row and column in which it lives. Right? What's the child? These 4. Huh? Some of them repeat. That's a coincidence.
Well, because it ends up being the same exact thing, just in different order.
Well, yeah, that's a coincidence. Yeah, Matt's noticing that we're getting another -10. That's just a coincidence. Some of the children are identical. In some problems, all the children are different. That's an interesting observation, though.
Well, yeah, because then the third one ends up being, when we get there, it ends up being 7. So it's
Oh, yeah. Yeah, it's a bit of a coincidence. Yeah. Okay, let's go ahead and fill this in now. What's the child here? We got a 2. We have 2. And we have a 12, and we're subtracting, right? Okay, so another -10. Another -10 baby. Okay, so another -10 right there. Okay, next is this guy. Notice that we're filling in the same space over on the matrix of minors. So if you're wondering, which one do I do next? Well, just look at which space you're in. That's sort of a roadmap of what you should be doing on the original. Okay, so we can cross out our mama row and mama column there. See the child? Here it is. All right, so multiplying those together, you should be getting a -2 and a -9, but remember you're subtracting. So that's what? 7. Good. 7 goes here. And Matt's right, row 1 and row 2 look similar in our matrix of minors, but that's just a coincidence. Okay, now let's go on to the last possible set of parents. So next would be this one, crossing out the row and column. Here's your children. We have a 6 minus a 12, so that's -6. There's a new number for you, Matt.
And then it's
Yeah.
a whole lot of rows all
Then we have this parent. Cross out the row and column. Here's your children. This gives you -4. Take away 4 more, that's -8. Sometimes you do get 0, by the way, for one of the children. It's always sad when a child is just a 0. But it does happen. It's rare. You shouldn't expect it. Your numbers kind of have to be perfect, you know. If you're getting a whole matrix of minors full of zeros, something very fishy about that problem. Okay? And the last one is, of course, the last possible parent. That spot. Cross out the row and column. Find the child. Find the determinant. We have 6. You're taking away -3. That's 9. That's step 1. Create a matrix of minors, a matrix of children. Okay? Everybody got it? Okay, step 2. What does step 2 say? Form a matrix of cofactors, right? Mock. Okay, I'm going to create a matrix of cofactors. Watch this. This is going to take me about 5 seconds. And I'm going to see if you can figure out how I'm doing it. Okay, on your marks. Get set. Go. Okay, I just did a matrix of cofactors. I made a brand new matrix using my previous one. It's sort of a mock version of that one. It's not the exact same, but it's very similar. What exact change did I make? Yeah, I changed the signs of just about half my matrix. See that? Which terms did I change the signs for? Every other one. Did I change the signs on the first element? I did not. I changed the sign on the second element, the fourth element, the sixth element, the eighth element, the even elements. Okay? So I like to call this the mock version of the previous one. It's kind of like a conjugate, you know? Sort of the opposite, but only every other term. I told you this was weird. This is called a matrix of cofactors. What you basically do is you just superimpose a checkerboard of minus signs on there. Okay? That's it. The reverse of checkerboard? You wouldn't want to do that. Unless you're the kind of person who does step 3 first. In a moment, we're going to make some more changes. But yeah, always make sure that when you superimpose your cofactors, to create your cofactors, when you slap your negatives in, make sure you do the right ones. It's the second one on the first row, the first and third on the second row, and then it's the middle one on the bottom. Just think like a checkerboard pattern. I'll draw the checkerboard for you. These are all positives. The minuses are every other one. Another way to remember this, guys, listen, is you'll notice so far I have not even touched this major diagonal. I didn't touch it at all. The 1, the -10, the 9, those guys are like a rock in this problem. They're not, no one touches those guys. Okay? So I didn't touch those from one step to the next. Those stayed the same. So that kind of helps you remember what to change and what not to change. Okay? Don't mess with the major diagonal. All right, next step says, what? Step 3, what does it say? Find the adjoint matrix. Now, I regret to inform you, there are other names for this. Transpose matrix, adjoint matrix, adjugate matrix. Listen, it's easy, whatever you call it. It's easy, easy, easy. See if you can figure out how I'm creating my adjoint matrix. Your marks, you say it, go. Okay, don't shout it out, right? But I made some very small changes here. There's a positive 8, not a negative 8. Sorry. Couldn't read my own handwriting. The last element in row 2 here is a positive 8, not a negative 8. Sorry about that. Can you see what I did? I will say that I did not touch the major diagonal. That thing has stayed the same. So what did I do? What happened, Josh? Flipped it. Yeah, I reflected it actually over the major diagonal. So basically think of this as a line of symmetry. Watch my hand. Okay? Watch my hands. These two guys traded spaces. These two guys traded spaces, and these two guys traded spaces. In other words, the whole thing flipped over this line. It's like this is a line of symmetry. We did a reflection. Okay? There's another way to think about it. The old first row is now the new first what? Column. See it? So 1, -7, -10 now shows up going downwards in the first column, because that was the first row originally. -1, -10, -7 shows up as the middle column. See? The last row is now the last column. So you can think of it as reflecting, or you can think of it as what we call transposing. Switching rows to columns, columns to rows. Okay? All right. Step 4. What does step 4 say? Divide each element by the determinant of the original. Okay, let's just go back and look at our original. Remember, our original was actually this. And some of you came in today saying, how do you find a determinant of 3 by 3? Let's just review that again. So we're suggesting now that we all make them fill in the blank if we're struggling. And there's a big fat mandatory plus, minus, plus here. We put the parents, those are the first row here. You take these guys and you fill these 3 spaces. And their children go in the other 3, right? The determinants of their children. So basically the children are going to go in these 3 spaces. Okay, so the child is 3 minus 2. This is a 1. This is a 7. This is a -10. Well, yeah, I already knew that. Those were just, we actually found those earlier. Those were the first 3 children back on step 1. Those were the first 3 children back on step 1. The green things there. This all comes out to be -17. Okay, so at this point you have 2 options, okay? You can take this step very literally and actually write -1/17, +1/17, +6/17, 7/17, 10/17. I'm going through and dividing every single term by -17. 10/17, 7/17, -9/17. Or, if that's too many 17s for your tastes, simply leave the -1/17 out front and put your adjoint matrix next to it, with the understanding that you'll distribute if you need to. I don't really like distributing those sorts of things. I mean, who wants a bunch of fractions? I'd rather have 1 fraction out front than 9 fractions inside, if you know what I mean. So, what do you guys prefer? Do you want to leave the 1/17 outside, or do you want to distribute it in? Okay. Totally up to you. If you decide to distribute it in, know that this matrix that you just created is very special. Okay? This matrix right here, whether you have the 1/17th inside or outside, is super special. He gets a very beautiful blue color. Why? Because he is the only matrix that can solve this problem. That is the inverse of our coefficient matrix. It's like when you get oil on your hands or grease on your hands, there's like one chemical that's the right solvent that will get that stuff off your hands, you know? I don't know, maybe it's hand cleaner, you know, that orange smelling stuff, that stuff's cool. But there's one chemical that reacts well with that stuff on your hands. And here, this is the solvent. This is it, the one matrix that will solve the problem. So are we done with this problem? No. We have the solvent. That's it. All right. Does everyone understand? Okay, so this guy right here is our solvent. He will solve the problem for us. We've got to take him back to the previous slide and stick him in. Okay? All right, let's do that. Come here. You shall go to the previous page. I like this page. Too bad. Tough noogies. We need you on the other page. No. You shall be pasted where that red thing is. You didn't even bring all of me. I'll fill the rest in. You know I wasn't going to remember it if I didn't copy and paste. All right. The strange world of digital surgery. Okay. So, there it is. This is the answer to our problem. We've got to solve it. Leave the negative 1/17 there. Let's do 3 dot products. Okay. So remember what you do with this. You take the first row as a vector, and you dot it with the first column of the second matrix as a vector. So it's like a dot product. And that dot product, you multiply the first elements, the second elements, and the third elements, and add them all up. Right? 8 and 3 and 6, those get added together. 8 and 3 and 6, obviously that's 17. All right? Now we're going to go on and do the second row vector, dotted with the column there. Now we've got a negative 56, we've got a plus 30, and a minus 8. So that was a negative 56, a plus 30, and a minus 8. And those add up to negative 34. Okay, our next one. This is an 8. The last one is the dot product of negative 10, negative 7, and 9 with 8, negative 3, negative 1. We have a negative 80, a positive 21, and a negative 9, which all combines conveniently to negative 68. And now we can finally distribute in the ugly little fraction, and we get the beautiful answer, negative 1, 2, 4. Oh, you got to love this method. Matrix of minors, matrix of cofactors, adjoint matrix, divide by determinant. But you asked for it. Somebody yesterday said, what about the 3 by 3 determinant? Or inverse. And I was like, well, let me go back and study that one again. So we've got it down to mom, mock, adjoint, divide, and dot products. There you go. This works on any number of dimensions. Now, can you tell me what would happen if you got to step 4 and the determinant was 0? You cry because you wasted your time on steps 1, 2, and 3. Do you think maybe it might be wise to do the determinant before you start the problem? Yeah. Just in case it's 0? If it is 0, that means one of many possibilities. Okay? it's three parallel planes, it's really only two planes, maybe it's all one plane, maybe it's like the planes don't quite cross in the right spots. It just basically means you can't use this method. Quit using this method. Go back, try row reduction, draw a picture, go on Wolfram Alpha and plot the planes and see, look at them. Look at the planes. You can do that with online 3D graphing calculators. You can see the planes. That's cool. You can even rotate them and see it real nice. Okay? All right. So there you have it. The last of the last methods. So the takeaway skill on that is we now know how to invert a matrix, which is useful all on its own. That you don't have to solve a system to invert a matrix.